Welcome back to Catalyst Grid. My name is Kingsley Imafua, lead scheduler with DC Nordics. Today, we are focusing on the critical bridging element of our power system, the 2N+1 Modular UPS. This is where we ensure the machine never stops. We are moving from the high-voltage generator yard into the heart of the data halls. This is Series 2, Episode 9, 2N+1 UPS, Modular Resilience at 85 megawatts. Building the machine at Hyperscale requires absolute, uninterrupted continuity. In Series 1, we looked at Iron Gate. Its UPS architecture was a standard 2N setup, two complete systems, each capable of carrying the full IT load. It was the correct engineering specification for a 10 megawatt Tier 3 facility, but at FULCRUM, we have moved beyond standard limits. FULCRUM, however, is a Tier 4 equivalent campus. We are managing 85 megawatts of critical IT load. This requires a 2N+1 architecture, two complete distribution paths plus a third, redundant string for absolute resilience. In this environment, downtime is not an option. The battery system is our bridge. It must support 20 generators through their 25-second start and synchronization sequence at a full 85 megawatt load for every single grid failure over the next 25 years. That is a lifetime of reliable performance. At this hyperscale, we've moved away from the fixed topologies used in smaller facilities. Modular UPS technology is fundamentally different, offering scalability and what we call redundancy in redundancy. It is a smarter way to manage power. A fixed topology uses large, monolithic units. In our modular topology, we use racks of plug-in power modules, typically 25 to 50 kilowatts each. This allows us to treat power like a modular IT component, providing flexibility we've never had before. While fixed systems have redundancy at the system level, modular systems provide N+1 redundancy inside each individual UPS. A module failure only auto-bypasses around itself, while all other modules continue to support the load without a ripple. Scalability is a massive commercial and technical advantage. Instead of being locked into a fixed capacity from day one, we can add modules to existing frames as the IT load increases. This is the pay-as-you-grow engineering model that fits hyperscale growth. Maintenance is transformed. Instead of requiring a full system bypass for internal work, we can hot swap individual modules while the UPS continues to protect the load. This eliminates a significant single point of failure and keeps our uptime at 100%. For a project like FULCRUM, modular is the only logical choice. The combination of scalability and hot swap capabilities is critical when managing critical backup power at an 85 megawatt scale. It is about future-proofing the machine. Each data hall has its own 2N+1 system. 3 independent strings, A and B, share the load 50-50. The C string is on hot standby, fully energized, battery float charged, but carrying no load until it is called upon. The C string is ready to pick up the full hall load within a single UPS cycle, less than 20 milliseconds, if either A or B fails. This architecture ensures zero interruption to our critical IT infrastructure, regardless of individual string faults. Now for the critical engineering question, how much battery energy do we actually need to bridge 85 megawatts for 30 seconds? The math is straightforward, but the resulting numbers are staggering and require careful consideration. Energy required equals power multiplied by time. 85 megawatts multiplied by a 30-second generator start window gives us 2,550 megajoules. That is approximately 708 kilowatt hours of raw bridging energy needed at the bus. But we must account for battery aging and worst-case extended start scenarios. By adding a 50% safety margin, our design capacity becomes approximately 1,100 kilowatt hours per data hall group to ensure reliability throughout the life cycle. That results in 4,400 kilowatt hours across the entire campus. This system can bridge 85 megawatts for over 45 seconds even under age conditions, providing a massive safety window for generator synchronization. This is engineering at scale. For our energy storage, we've specified lithium-ion LFP technology. Lithium iron phosphate offers significantly higher thermal stability than traditional NMC chemistries, making it the only acceptable hyperscale standard for our mission. The design life is 15 years to 80% rated capacity, with a full campus-wide replacement planned at year 15. Temperature control is absolute. We maintain operating conditions between 15 and 30 degrees Celsius to maximize performance. Each battery room has dedicated HVAC providing 10 air changes per hour minimum. We monitor for thermal runaway gases, specifically hydrogen and carbon monoxide, with high sensitivity integrated sensors tied to the emergency shutoff. BMS monitoring tracks every single cell's voltage and temperature. This data feeds into our DCIM in real time, allowing our operations team to track remaining autonomy down to the exact second for total situational awareness. Safety in a lithium-ion battery room requires specific design decisions, not general assumptions. We must address the risk of thermal runaway, an exothermic reaction that can exceed 600 degrees Celsius and lead to catastrophic failure if not managed. LFP chemistry has a much higher thermal stability threshold than NMC. While thermal runaway releases flammable gases, the threshold is higher and propagation is slower in LFP, giving our suppression systems critical time to respond and contain the event. Our suppression strategy is CO2 total flooding. CO2 is specified because it absorbs heat and reduces oxygen concentration. Clean agents like Novec or FM200 are simply not effective against lithium-ion thermal runaway events once they start. Clean agent cannot suppress LFP thermal runaway. Our protocol is clear. The room must be evacuated and sealed, and then flooded with CO2 to allow the system to cool down naturally and safely. It is the only way to protect the facility. Each UPS string includes a static transfer switch, the STS. This allows for an instantaneous transfer from UPS output to raw mains in under 4 milliseconds if a critical fault is detected in the inverter, bypassing the modules entirely. A maintenance bypass routes power around the entire UPS for physical access. At FULCRUM, this requires written authorization from Cloud Core, as the load is unprotected from grid disturbances and transients during this period. Risk must be formally accepted. It is time for the series signal. Always specify LFP chemistry for data center lithium-ion batteries. Its thermal stability advantage over NMC is material and critical for overall facility safety and mission-critical performance. And always specify CO2 suppression in battery rooms, not clean agent. This isn't a preference. It is the only correct engineering response to the unique hazards of lithium-ion thermal runaway at hyperscale. Don't compromise on safety. In episode 10, we move to campus cooling. We'll look at airside economization, adiabatic pre-cooling, and waste heat recovery systems that deliver our campus PUE target of 1.2. The machine must stay cool to stay fast. Thank you for joining me on this deep dive into modular UPS resilience. Building these machines requires precision and an uncompromising commitment to safety. I am Kingsley Imufua, building the future of power. Don't forget to subscribe, like, share, and comment below. Your engagement helps us build this community of hyperscale engineers and share these insights with the world. I'll see you in the next episode. Thank you for watching Catalyst Grid, building the machine at hyperscale. Keep building, stay safe, and goodbye for now. This technical documentation is intended for professional use within the DC Nordics and Cloud Core engineering networks. Confidentiality status remains active for all technical specifications presented. For further inquiries regarding the FULCRUM power architecture or 2N+1 UPS configurations, please contact the DC Nordics lead scheduler team directly, building the machine at scale. Thank you for your commitment to engineering excellence. Catalyst Grid will return with episode 10, Campus Cooling and Heat Recovery. Technical documentation concluded.